Today, we're diving into one of the trickiest, most fascinating problems in all of technology. How do you protect a self-driving car from a danger you can't even imagine? A danger that nobody's ever thought of before.
So, let's start with a question that sounds, well, a little bit like a riddle. Can a car with zero faults, no bugs, and absolutely perfect hardware still be dangerously unsafe out on the road? The answer, incredibly, is yes, and understanding why is the absolute key to the future of autonomous vehicles.
You see, this forces us into a whole new way of thinking about safety. For 100 years, car safety has been about fixing things that are broken. A bad brake line, a software glitch. But now, we're facing a totally different challenge. How do you guarantee safety when a system is working exactly the way it was designed to?
To solve this, the industry created a standard called SOTIF. It stands for Safety of the Intended Functionality. And unlike traditional safety, which is all about malfunctions, SOTIF is obsessed with the dangers that come from a system's own limitations, or from just the sheer weirdness the real world can throw at a car.
Okay, so if you're an engineer, how do you even start to wrap your head around a problem this big? Well, the first thing you do is you draw a map. You need a way to chart out the entire universe of possible driving situations just to see what you're up against.
And what's so cool about this is how simple the map is. You can literally plot every single thing that could ever happen on the road using just two axes. First, is this situation something the developers know about, or is it totally unknown? And second, is the outcome of that situation safe or unsafe?
This grid lays out the entire battlefield. Area 1 is your happy place, situations we know about and we know are safe. Area 2 is for the known dangerous. The engineers have identified a problem, and now they had to design and test a solution to move it over into Area 1. But the one that keeps everyone up at night is Area 3, the unknown and unsafe. This is the real danger zone, the home of threats that no one has even conceived of yet.
These Area 3 scenarios have a name. They're called black swans. It's a perfect analogy. For centuries, people in Europe just knew that all swans were white. The discovery of a single black swan in Australia instantly shattered that fact. These driving scenarios are the same. They're rare, they're unpredictable, and they can have a massive, catastrophic impact. These are the beasts that SOTIF was designed to hunt.
So, if a danger is unknown by its very definition, how in the world do you find it? It sounds impossible, right? Well, this is where the SOTIF toolkit comes in. It's a whole collection of clever methods designed for one purpose: hunting for black swans. And engineers have some really fascinating tricks up their sleeves. They're not just driving around hoping something weird happens. No, they are actively trying to break the system. They'll do things like create fake ghost targets on the radar, use data from thousands of cars to find those one-in-a-million events, and they'll even bring in naive users, people with no experience, just to see what strange and unexpected things they might do with the car.
Now, one of the smartest techniques is something called performance insufficiency injection. This is just brilliant. Instead of spending forever trying to perfectly simulate every kind of bad weather, thick fog, blinding sun glare, torrential rain, they just skip all that. They simulate the effect of that weather directly on the car's sensors. They just feed the system noisy, garbled, low-contrast data and see if it chokes. It's an incredible shortcut for finding hidden weaknesses.
So as the engineers are running all these tests, they have a way of categorizing the problems they find. And it's a really crucial distinction, the difference between an edge case and a corner case.
An edge case is pretty easy to understand. It's what happens when you take one single thing and push it to its absolute limit. Think about testing the car's camera in the darkest possible night it's supposed to work in, or slamming on the brakes at the fastest speed the car can go. You're testing the very edge of what it can do. A corner case, though, is way more sneaky. This is a problem that only pops up because of a rare combination of different things happening all at once. And here's the kicker. Individually, each of those things might be totally normal. The speed is fine, the rain is just a drizzle, the sun is out, but all together they create a perfect storm that completely confuses the system. These are a nightmare to find because you can't predict them.
So let's just put it side by side. An edge case tests the known boundary of one thing. A corner case tests the chaotic, unpredictable interaction between many things. Finding edge cases is methodical. Finding corner cases, well, that's like looking for a needle in a multi-dimensional haystack.
And all of this leads to the biggest, hardest question of all. You can hunt for these black swans forever, but how do you know when you're done? How can you possibly prove that you're safe from the dangers you didn't find? The answer isn't about driving for a billion miles. It's about math. It's about probability.
Engineers use this model, this chain of events you see here, to figure out the actual odds of some weird trigger event cascading all the way down the line to actually causing harm. Let's break down what each of those links in the chain really means.
Now, I know that formula looks a little intense, but the idea is super simple. Just think of it as a chain of what-ifs. For instance, let's say a plastic bag blows across the road. What's the probability of that triggering event even happening? Probably pretty rare. Now, given the bag is there, what's the chance the car's system freaks out and behaves badly, like swerving? Then, if it swerves, what's the probability that leads to a real accident? By multiplying all these tiny probabilities together, step by step, the final number for the overall risk gets incredibly small, incredibly fast.
And that brings us to the most important point. The goal is not the impossible task of eliminating every single risk. The goal is to test and analyze and hunt until the engineers can build a rock-solid, evidence-based case, what the standard calls sufficient confidence that the leftover risk from all those undiscovered black swans is acceptably low.
And really, this is the big takeaway for this whole process. SOTIF is not a fantasy quest for perfect, absolute safety. It's a realistic, pragmatic, engineering-driven process. It demands that you prove you've mastered the dangers you know about, and that you've reduced the odds of the unknown dangers down to a level that we, as a society, can accept.
Which of course leaves us with one final very big thought. This whole system is built on the idea of being safe enough. But that leads to a question that goes way beyond engineering. For a machine that drives itself on our roads, among our families, what does safe enough actually mean? And maybe more importantly, who gets to decide?